There's a microphone.
I got a microphone, yeah.
Okay, great.
Cool. Thank you for having me. I'm Bennet, and I can skip slides. How do I skip slides on this thing? Ah, left click, okay. If you don't know how I look like, that's how I look like. I like cows. I like small cows, and I like big cows. I like data storage cows. This is my office. This is where I work. You can see I'm sitting right next to a giant window and the sun shines in. And it gets super, super hot in our office in the summer. I was wondering how hot does it get? So I sat down and measured it. You can see it gets really hot, over 27 degrees. What I really like about this graph is that you can see in the middle this little notch. That's where the neighboring skyscraper casts a shadow on our office. So it's like 1 hour of a bit cooler, and that's really, really nice. How did I measure this? Well, I took the NRFDK development kit. It has a little temperature sensor wired into the sock, so I can just use that. And then transported the data over the UART via USB. And the next question is, of course, how do you actually measure the temperature, right? You have to build software for that. And the easy option is to build a RIOT application. That's easy, but it's also difficult, and you have to think and do work and program. And I'm lazy, I don't do that, right? So I thought, what's the next easy way, the next lazy way to do it? And RIOT offers a shell. And the shell is a soul command. And the soul command can read arbitrary sensors for you. You just have to know how to use it. So I thought, hey, what about a simple shell loop, right? You have the bash, you have your /h, whatever, and you have a one-liner of bash script, just piping the soul command into the RIOT shell, logging the temperature, and repeat. That's all you need to do. So I opened up the RIOT shell and was like, okay, soul-help, how do I use this thing? You can see you can read and write, so you can also set actuators, very cool. So I ran soul read-help, and I got back the state of my button 1. If you're confused now, that's okay. I'm also very confused. And that is always the first problem we have with the RIOT shell. It's not that easy to use, right? I mean, it's not difficult, but also you can see it has its flaws, right? The head messages are all over the place. The argument order is always different between all the commands. Some commands take complete URLs, others only take the host part. It's very confusing. So I asked an expert how to use soul, and he was like, oh, it's easy. Just go soul read, and then put the ID of the sensor you want to read. The temperature sensor in this device is ID number 8. I was like, cool. I typed that in, I press enter, and I get the temperature. Except I didn't. I got back a packet snip because apparently on my application in the background, there was a thread running called packet dump, and it received a network packet and was just dumping it directly to the user through the shell. That's inconvenient, but if you wait long enough, you actually get the temperature back. So great. You can see it's 41 degrees in my office. Don't panic, it's not actually the temperature in the office. I was just shorting pins by accident to have a nice number for the slides, right? And this is always the next problem we have, right? We don't really have a matching between the input and the output. I mean, for a human, this is okay-ish to parse. You can figure it out, but it's annoying, right? You cannot really trust what you get after you type something in. The next problem is, of course, the syntax and semantics. I think I can write a parser that can actually figure out the temperature from this result, but it will always be brittle and annoying. And I don't want to write a parser, right? I just want to get the temperature back and don't have to work about all of this. And there's a fourth problem. You can't really see it on the slides, but we never really know when we are done, right? The RIOT shell doesn't really offer a way of telling, hey, the command completed. Did it complete successful? Is it still running? You don't know, right? That sucks. So yes, I could probably build a shell one-liner that can use the RIOT shell, but it will be annoying and it always kind of sucks. Luckily, we have a secret option, option C. What if we have a better shell that actually doesn't have all these problems? And I got very, very lucky because actually such a shell exists because I built it. And I called it Jelly. Here you can see the terminal user interface. Don't get scared, it's a lot of information. We will break it apart. So I select the image by accident, and then I skip to the next slide. What exactly is Jelly? And to answer that, we take one step back further and ask what actually is the RIOT shell, right? Because the idea of the RIOT shell is that you have a user and a RIOT device, and then you have some kind of human-friendly interaction. I don't know what humans say, something like hello, goodbye, whatever. And the RIOT device and the shell have to figure out what did the human mean by it, then do the computation, gets the result, and then converts the result back to something that humans can read. But this diagram is actually lying, because that's not what's happening. In reality, it looks like this, right? We have human-friendly interaction between me and my development machine. But what my development machine is talking to RIOT, I don't really know. Maybe it's machine-friendly. I mean, ASCII is some kind of machine-readable standard, if you want to say it like that. But yeah, we are very, very open in what we actually speak to the RIOT device. And this is where Jelly comes in. Jelly really is just like a translation unit between the human language and the machine language. That's the idea behind it. That's what I'm trying to target at. Now, how would we build something like that? Well, the first thing is very easy. We need machine-friendly communication. And the RIOT device is a constrained device. So we need a constrained application programming language or a protocol. And one good candidate for that is CoAP, right? CoAP has a lot of nice features. It, for example, has request and response models, so we actually know when something completed and we got data back. But there's an issue with it. RIOT is full with printf statements and debugging statements. We already have the RIOT shell. And if we move to CoAP, those don't work anymore. And of course, we could whip them out of RIOT and throw them away. But I don't want to do that, because this is code that is already there and works and is tested. So why throw it away? You could go ahead and try to funnel those statements, this printing, through CoAP. But this is not the solution that I really, really like, because if you want to have std out over CoAP, you would have to buffer the std out, and this introduces inherently some weird behavior that's hard to explain to a human. And I really wanted to keep it easy for the human without any difficult to see and understand behavior beneath it. So I was like, what if we just don't do that? And instead, we just continue to stream the strings as they are between the RIOT device and the host computer. Now, just for good measure, we also throw network into it, because network is always nice. Everyone loves network. But for this presentation, this is out of scope and just a bonus feature that I implemented. And now we have to solve a problem. We have the UART, and the UART is a streaming connection. And we have 3 different types of packages that we want to transmit between it. So we need to multiplex and to do framing. I didn't have to invent it, because other smart people already invented something like that. It's called Slipbox. The idea is from the University of Bremen, Carsten Wormer, you might have heard of him. And it does exactly that. Just framing, escaping, and multiplexing on the serial connection. So that solves all my problems. Because we have UTF-8 strings, we are fully backwards compatible. We still have printf debugging. We still have logs that keep working. Even the RIOT shell completely keeps working. We have to don't change anything at all. Just everything works. And because we have CoAP now, we can shift the computation from the device onto the host machine. We can define the CLI on the host machine. We can do the argument parsing on the host machine. We can print the help messages on the host machine. So we can also have very verbose help messages that don't suck, that don't get interpreted as actual data. And once we interpreted the command, we can just query a CoAP endpoint, get the response, and then we translate the response back to the human language, all on the host. So the RIOT device has less work to do, which is great. Now with CoAP, we get a lot of benefits. Most are probably obvious to you guys because you know CoAP. But of course, we now have a copied input to output. We have the quick request and response matching. We can now tell if a command is still running or if it's finished, because you can see if you are still waiting for responses, we still need to do work. Once you have a state for your commands, you can have asynchronous commands, right? Now we can insert multiple commands at the same time in parallel. As long as we don't exhaust the little poor RIOT device, we can arbitrarily do that. And lastly, for me, my favorite part of this, we can now work with binary data, because we are now transporting binary data between the RIOT device and the host machine. And what we do with the binary data is up to us, the user. I really like that. Right, now let's look into how does it feel like to use Jelly. I don't really want to show the Jelly in general, because if you're interested in using it, I have a demo outside, you can play with it, but just to get the feeling across of what you can do with this kind of tool, right? And the first thing I'm going to show you is you don't have to use the terminal user interface at all. You can do it completely headless. And this is important, because if you do it headless, you have a 100% backwards compatible drop-in replacement, for example, for Python or Minicom. This even works with the RIOT test for the shell. I already tried it. it's nice. So you don't need to worry that suddenly, because you have all this TUI and slipmux, that the old way doesn't work anymore. Nope, 100% backwards compatible. Next, let's take a look how it feels like to use the terminal user interface. Now I really would like to show you around and show you how awesome this is, and that we have autocomplete and the proper command history and different views depending on the context of the user. But my time slot is really, really short. So I want you guys to focus on the lower left corner. You can see I executed the so read command. This time, the new version in Jelly that uses CoAP under the hood. And I executed that so read command 3 times. The first time, just like that, I get the temperature back, just as before. The second time, I executed again and asked Jelly, hey, export that result to a file, please, temperature.txt. And the third time, I executed again and said, hey, please export binary for me and save that. And Jelly's like, okay, I can't display binary to you, but I can give you a hexagram at least. And once we've done that, we can close Jelly again, go to the temperature.txt file that we just created, cat on it, and we can see the temperature. But of course, we can now also cat the temperature.zero that we created. I cannot look at zero with my eyes, so I've piped it over to zero EDN and convert that to the diagnostic representation. And we get that result back. This is actually not a format that I invented. This is sensor measurement lists. It's a little RFC that tells you how to format the sensor values and actuator values. Really, really cool. And now we have all the building blocks that we need to build a bash one-liner to actually read the temperature over and over again. Let me just quickly get it big. Right. So now I have got everything I want, and I can now finally log the temperature, reliable, without programming, very, very lazy, and I love it. This is the solution to the problem. Now I'm building something new. I'm entering a new area. And every time I do that, I try to stop and take a look around. Because if you go somewhere new and nobody else is there, you might just be walking in the wrong direction. And I don't want to walk in the wrong direction because that's embarrassing. So let's set a bit of context and see what others are up to. First, RIOTers. RIOTers doesn't have a shell, but they have logging. And this logging is very, very nice. It's very verbose, like really verbose. I have to truncate a lot and pretend this fits on the slide. And they can do that because they use deferred formatting. Long story short, they don't really save the strings on the device, just some keys, and then have a lookup table on the host and blah, 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 blah. But for Jelly, this tells me people are interested in having not the strings in the device and save that storage for something else. And that people are interested in having a verbose output, right? So I think for Jelly, this means, oh, roughly the right direction. People are interested in that. Let's take a look at Sapphire OS. Sapphire has a shell built in, and it's really, really nice. It's a great user experience. It has proper help messages. The argument parsing between the sync commands is somewhat coherent. It has autocomplete. It's a nice experience, but it's completely on the device, on the constraint device, and Sapphire is already quite big. So I think for RIOT, this would be a deal breaker, having such a comprehensive shell on a constraint device. But again, for the context of Jelly, this says, hey, people are interested in having good shells to work with constrained devices. They like a good user experience. They like modern features like autocomplete. Once again, I think I'm walking in a good right direction. Lastly, take a look at PostStation, because PostStation is a bit of an outlier here. PostStation is nice open source, non-operating system. It's a host application with a terminal user interface, just like Jelly, which talks to embedded devices and does remote procedure calls to get data back. And this, again, for me shows, hey, cool, other people are building similar looking tools that do similar stuff, not really the same, it's not a shell, but the general feeling of having an easy way to get binary data back from your constrained devices seems to be interesting. Yeah, I'm almost done with my presentation. There's so much I would like to talk about, like how does Jelly's architecture look like? It's written in Rust. How does it feel like to build a new Rust command for Jelly? I think CoAP should be mentioned here as a constrained RESTful application language, because I don't really want to build custom endpoint handling tools, but have it in a more semantic way. But with the time I have left, I just want to show one tiny thing, and it's this. You can see the Jelly terminal user interface again, but it's not connected to RIOT, it's connected to RIOS. And that's because Jelly doesn't really care what it is talking to, as long as it's slipmux and has interesting CoAP endpoints, and then we can talk to it. So if you imagine RIOS would also implement sensor measurement list like RIOT does, the soil command would just work also with RIOS, just like that. So I think that's an interesting opportunity. Yeah, if you want to try out Jelly, get it on GitHub. If you want to integrate Slipmux to your project, I have a crate available, MIT license. And if you want to play with it, I got a demo sitting right there on one of the desks. Go play with it, give me some feedback. Thank you.
For the presentation, what you mentioned about macro compatibility, this is just using Jelly, right? Or you mean that basically when you compile such an application, you could also just like get the same shell output, because if you're using Slipmux there, I guess you still need you can still use a shell, but through Jelly.
Yeah, exactly. If you're using Slipmux driver, then you can use Jelly in a 100% backwards compatible way to the current setup. Yeah, so you don't need to worry to break all setup just because you enable Slipmux. You can still do it.
But you're still using Jelly. So you change basically the shell, the output of the.
Yeah, exactly. Okay.
I was wondering whether there's a way to look at this differently, more from a debugging point of view as a shell, not just a regular shell, because normally depends on what you want to do. But if you look at what other people did with debugging, rather than just piping out some printfs to provide actually something more sophisticated. There are tools like dedicated commercial tools, there are tools from ARM, likewise, where you put something in memory, or even core side or something to get a couple of inspiration there. So I think there's potentially a possibility to do more than sort of like the extended version of printf. Like you write it in a buffer. So if you, depending on how intrusive you want to be, streaming variable changes, for example, for if you want to do debugging of systems in real time, or back traces, like you can instrument the code and so on. So there's a lot of probably a lot of options. There would be more sophisticated. But,
yeah, I think that's you could use Jelly for that. It's not what I have in mind. But remember, we have CoAP, right? If you want to observe a variable, you could just have a CoAP endpoint for the data that you want to observe and just do a CoAP observe, and you're done, right? Now you would only need to implement something in Jelly that actually can handle the data and replace it. For example, I have for testing a memory read command where I can just export arbitrary memory addresses with arbitrary amount of memory to my host machine over Jelly, just for poking around. It works really nice.
Any more questions? Hi, I'm Greg Content. If I wanted to create my own command for, let's say, Jelly, if I, for example, an application and want to print some stuff in a special order, how complicated would it be to add that command to Jelly?
That's a bit of a difficult question, because Jelly is a very new project, it's still changing. I put a lot of effort in so that you only have to implement two little traits in Rust to make a command working. I don't think it's difficult, but I'm already doing Rust for like 1 year now. So I think the more interesting part is how do you integrate it on the RIOT side with the CoAP endpoint, because that can get a bit tricky depending on what you're actually doing, because CoAP usually expect you to have some kind of application idea behind it, right? But I think it's okay, it's moderately. It's not that easy anymore as printf debugging, but you can always still do printf debugging because I never removed that feature.
Could we have other transports than single connections? Like
yeah, absolutely. Slipmux really does just framing, escaping, and multiplexing, always string connection. For example, Jelly can out of the box work with Unix sockets as well, because that was very convenient for me to debug and try to build this application. So yeah, if you go ahead and find something else that's in stream, you can do that.
Also tried that already, it works.
I actually also have one question. What implementation are you using?
Right now, I use a very hacky version of nano CoAP, and it's terrible and it doesn't support observations or anything. But I've spoken with Carl a lot, and I'm very, very happy that as soon as UniCoAP drops, I can implement it, and that will be very, very nice, because as you just seen in the other presentation, UniCoAP will be the first CoAP stack that actually has transport agnostic, so I can finally insert slip nodes as transport.
Okay, thank you, Bennet.